Ladies and gentlemen, if you could take a seat. We have some people following us online too, so we always like to start on time. Your Excellency, Ambassador Mitsukoshi, distinguished speakers, dear colleagues and friends, it is a great pleasure to welcome you to the Royal Swedish Academy of Engineering Sciences for this seminar on semiconductors, and in particular to welcome our distinguished guests from Japan. This seminar forms part of what we call the Top Scientists Lecture, a collaboration which we have had for several years now between the Embassy of Japan and Sweden, JSPS, the Sweden-Japan Foundation, the Swedish Foundation for Strategic Research, and the Royal Academy of Engineering Sciences. And it is a tradition and a collaboration that we value very, very highly. So we're very happy to welcome you to this seminar. Also, I would like to say a warm welcome to the people who are following us online. Today's event is a clear expression of the strong and growing relationship between Sweden and Japan in science, technology, and innovation. A collaboration and a relationship which I think the importance of which is only increasing as time goes by and for every day, especially in this new geopolitical context that we are operating in. EVA's mission is to strengthen Sweden's long-term competitiveness, sustainability, and resilience by bringing together academia, industry, and policymakers. And few topics illustrate that mission better than semiconductors. Semiconductors are not simply components in electronic devices. They are enabling technologies, foundational technologies that underpin almost every modern system. Electrification, digitalisation, artificial intelligence, advanced manufacturing, 5G and 6G, defense systems, green mobility, none of these developments are possible without high-performance semiconductor technologies. In other words, enabling technologies determine the pace and direction of technological development. They shape our ability to compete economically, deliver on climate goals, build resilient energy systems, and strengthen societal and national security. This is why semiconductors today are not only an industrial sector, they are a strategic domain. The green transition is fundamentally dependent on semiconductor innovation. From electric vehicles to renewable energy integration and smart grids, semiconductor performance directly impacts carbon emissions and energy use. At the same time, semiconductors have become a strategic technology in a geopolitical sense. Recent years have shown us how vulnerable global supply chains can be. Access to advanced chips, materials, manufacturing capacity, and talent is now closely linked to economic security and national resilience. This means semiconductor policy is no longer only industrial policy, it is also security policy. No country can master the entire semiconductor value chain alone. Strategic partnerships are therefore essential, and they must operate on several levels, between academia and industry, between fundamental research and industrial scale-up, between technology developers and policymakers, and crucially, across national borders. Japan plays a pivotal role in the global semiconductor ecosystem with world-leading expertise in materials, manufacturing equipment, and advanced research. The deepening cooperation between Japan and the European Union, including Japan's close association with Horizon Europe, creates important new opportunities for joint research and innovation. In a time marked by fragmentation and strategic competition, trusted cooperation between like-minded partners such as Sweden, the EU, and Japan is more important than ever. Sweden is a relatively small country, but we have strong assets in this field. We have internationally recognized research environments, strong industrial actors, and expertise in areas such as material sciences, power electronics, system integration, and advanced manufacturing. At EVA, at our academy, through our vision project called Swedish Futures, we have recently launched a dedicated track on semiconductors. The purpose is clear: to assess Sweden's strengths, identify strategic opportunities, and understand how we can contribute to and benefit from the rapidly evolving global semiconductor landscape. The message emerging from this work is encouraging. Sweden has excellence and significant potential, but realizing that potential requires coordination, long-term strategy, international collaboration, and ambition. Today's program brings together exactly what is needed: research excellence, industrial strategy, policy perspectives, and international collaboration. Semiconductors are a strategic technology for competitiveness, sustainability, and security, but perhaps even more importantly, they're an enabling technology for the future societies we want to build. With that, it is my great honor to welcome His Excellency, the Ambassador of Japan to Sweden, Hideaki Mitsukoshi.
Good afternoon, everyone. Distinguished guests, distinguished professors, guests, my name is Hideaki Mitsukoshi, Japanese ambassador to Sweden, as introduced. As one of the co-organizers of this top scientist lecture, I would like to say a few words. Sweden and Japan have both special places in the world of science, technology, and innovation. There are active collaborative research between universities in Sweden and Japan, and those exchanges are producing creative results. At the government level, the importance of academic exchange between the two countries has been repeatedly confirmed. This top scientist lecture, which was originally developed in 2014 by the IVA and the JSPS in order to introduce prominent Japanese researchers to Sweden, is a perfect example of such a partnership between Japan and Sweden. In Japan now, we have a new government since October last year, and our new Prime Minister, Ms. Sanae Takaichi, is very keen on the promotion of science and technology. Her administration made a huge decision to add 400 billion yen, or 20 billion euro, as a supplementary budget in research, soon after her taking a role as the Prime Minister last year. In addition, she has committed to increasing the budget for basic and fundamental research from next fiscal year. I believe one reason is because she served as Minister for Science and Technology in the past, and she knows this subject. But also another reason is that she was convinced by the two Japanese Nobel laureates about enhancing the environment for science and research. I remember those Japanese laureates have eloquently spoke about the need for more budget for basic science and research environment. And yes, so this is a good illustration of how Nobel Prize is contributing to the development of science and technology in the world. Today is a 4th year anniversary after the full invasion of Ukraine by Russia. The invasion brought so much change in geopolitical situation in the world. And one of the changes is the need for economic security. It is more needed than ever, and today's topic, semiconductor research, is an excellent topic for such an age. Semiconductors are indispensable material in our daily lives, and the importance of securing semiconductors has been increasing in recent years in many areas for the sustainable development of our economy. In this regard, production of semiconductors jointly with trusted partners is very important. in this context of economic security. At the same time, doing collaborative research in semiconductor is with trustable countries like Sweden is also crucial. Today, IBA and JSPS and our embassy invited Professor Tsunenobu Kimoto from Kyoto University. I understand that he is an expert in research on especially the reduction of energy consumption of semiconductors. And I learned from him that he spent 1 year at Linköping University in the 90s. And this time, he met many of his old friends in Sweden. Through today's lectures, I'm looking forward to learning about the current situation of semiconductor research in Japan, Sweden, and seeking potential collaborative work in this area in the future. I would like to express my sincere gratitude and respect to today's lecturers, Professor Kimoto, Professor Lash, Eric Vernation at Lund University, Mr. Ryohei Gamada at JETRO London, and panelists and all of the co-organizers for this event. Tack så mycket.
So, Your Excellency, distinguished guests, colleagues, ladies and gentlemen. I'm Stefan Bengtsson, and I'm connected to Chalmers University of Technology, and I will try to moderate the seminar during this afternoon. I'm also chairing the working group on semiconductors here at IVA in the work for Swedish futures that Sylvia mentioned a few minutes ago. So we now will have 3 keynote speeches, and the first will be given by Professor Kimoto. He's a Japanese electrical engineer and professor specializing in wide bandgap semiconductors, particularly silicon carbide materials and devices, and he is at Kyoto University. He is recognized globally as a leading expert in silicon carbide technology with contribution to its growth, characterization, and application in high-power electronics that enable efficient energy conversion and reduced environmental impacts. So, Professor Kimoto, please.
Thank you. Okay. So, thank you, Stefan, for kind introduction. And first of all, I'd like to thank or express my deepest gratitude and respect to all the IVA and JSPS people, especially Sylvia and the Kuroda Sensei for inviting me. Thank you very much. And before, maybe I have to send, okay. Before starting my presentation, I have to describe one important statement. Silicon carbide, this is my life work and the subject of today's talk. Silicon carbide was first synthesized here by Swedish chemist, Dr. Berzelius. You can see the statue, his statue, maybe within the 5 minutes walk from here. So all our work on silicon carbide rely on his invention 200 years ago. That's amazing. So anyway, he outlined my presentation today. In the first part, I will briefly describe the power semiconductor devices, and then I will introduce the rise of silicon carbide and show you the present status and impacts of silicon carbide devices. And finally, I summarize my talk. So this needless to say, semiconductor is a core technology for daily life and industry, and also the energy. And semiconductor is a broad field, covers really broad field. We can find many different kinds of devices. And one typical example is CPU or logic devices and memory. And the second one is many kinds of light-emitting devices or sensors, and also the solar cells. And third one is power device, which correspond to the muscle in the human body. And where can we find the power semiconductor devices? One typical example is AC adapter. Here, the input of AC adapter is AC 100 volts in Japan. Here maybe the double. And output of AC adapter is DC and low voltage. So you must experience that this AC adapter gets hot during charging. Do you know the reason? About 10% of electric power is lost inside the power semiconductor devices. That's a huge loss. And we find many other examples. For example, charging the EV or hybrid EV, of course, the source is high voltage AC, but battery is, of course, DC. And by using this DC battery, we have to drive AC motor. Many different kinds of AC and DC conversion. And then next example is solar cells. Of course, solar cells generate DC power, but to connect the power lines, we need AC. So always we have AC and DC conversion, and always we lose 10% power. That's a huge loss in the world. So we try to cut down this power loss as much as possible. And this is a schematic current and voltage characteristics for ideal power switching devices. I mean the transistors. This is too much ideal. In the on-state, high current with 0 voltage drop. And off-state, high voltage with no current. But this is too much ideal. And reality, we have this kind of characteristics. In real semiconductor devices, of course, we have maximum withstand voltage we called breakdown voltage here. And on the on-state, here the slope, which correspond to the we call on-state resistance. So this resistance is the main cause of Joule heating, which means power loss. So yeah, I'll skip some technical details, but we have to fight with this trade-off between on resistance and blocking voltage. For example, for AC adapter or the EV, we need 600 volts or 800 or 1,000 volt devices, transistors. Then when we increase the blocking voltage, then the on resistance is going up. This is a very severe trade-off. And what's silicon carbide? Silicon is the king of semiconductors everywhere. And carbon, diamond is hardest material due to strong chemical bonding. And silicon carbide consists of 50% silicon and 50% carbon. So this is hard semiconductor, wide bandgap. And silicon carbide is known as a moissanite in the field of gemstone. And you can find these kind of pictures on the internet, many, many pictures. And they say that this is the most brilliant jewel in the world. This is scientifically correct. Main reason is wide bandgap, so the silicon carbide is transparent against the visible light, and refractive index of silicon carbide is higher than the diamond. So we make some same brilliant cut or stone. We have more optical reflection from silicon carbide than diamond. And now I will show you later, we can grow very large ingots. So the cost is very low to make such gemstones. But unfortunately, less expensive gemstones are less attractive for ladies. So it's always difficult to capture the lady's heart, okay? So anyway, the gemstone, that's not my business. Semiconductor devices. One slide about the technical details or physics. Yes, anyway, we need handle the high current and high voltage. But high current means chip size. We can enlarge a chip size to get delivered high current. But breakdown voltage, which is associated with a little bit semiconductor physics. This is a typical distribution, schematic distribution of electric field inside the semiconductor devices, like diodes or transistors. This is the case of silicon. And each material has some inherent maximum withstand electric field we call breakdown field strength. The breakdown itself is determined by electric field, not voltage itself. This is the physics. So this is maximum field, and here electric field versus distance. So the area of this triangle corresponds to the breakdown voltage. With silicon carbide, this maximum or breakdown field is about 10 times higher. So we can get the same area of triangle by using this vertically sharp one. So clearly, the required thickness is only 1/10 in silicon carbide. And more importantly, this slope of this triangle corresponds to the doping concentration. Some professional term. So we have more electrons, so low resistance. So as a result, when we compare the silicon device and the silicon carbide device with the same blocking voltage, then onset resistance of silicon carbide devices is about 500 times smaller than silicon. It's really promising for reducing the power loss. And this is the real trade-off between the resistance, which corresponds to the power loss, and breakdown voltage. This is a silicon limit, and this is a silicon carbide limit. So we can reduce the resistance of the power at a fixed or given blocking voltage, or we can go to the 10 times higher blocking voltage with a given own resistance. So the rise, it looks very promising, but in reality, we encountered numerous difficulties or problems. In 1990, when I started silicon carbide work, no wafers are commercially available. The silicon or gallium arsenide, they have disc-shaped, high-quality material. This is the base material. Without these wafers, nothing to do. So we had to grow the wafers by ourselves. But we don't have any seed crystal. And then we picked up these very funny crystals. This is formed by as a byproduct during the manufacturing the silicon carbide abrasive powders. And we picked up one piece as a seed and grow some small ingot like this. But after making this ball on back, and I had to slice the ingot. But as I mentioned, the silicon carbide, very hard material, so it took almost 1 week simply for polishing. So the progress is so extremely slow at that time. And another topic is that in 1990, almost nobody considered silicon carbide is promising for power devices. At that time, the main target of silicon carbide semiconductor was blue LEDs. At that time, gallium nitride and zinc selenide and silicon carbide were competing toward blue LEDs. And the winner, gallium nitride. And they received a Nobel Prize in physics about 10 years ago. So after this invention, silicon carbide lost the significance or the value. But I and my supervisor, Professor Matsunami, started silicon carbide power devices at that time. So if you're interested, please have a look at this brief article published in Nature Electronics I describe some early history of silicon carbide. So another problem is polytypism. Silicon, the king of semiconductor, only single phase. Silicon, only one phase. And gallium arsenide, similar, only one single phase. But the silicon carbide, we have many, many brothers and sisters, more than 50 or almost 100 different crystal structures. Why is that? Please consider the cross-packing system in a crystal. This is a sphere, and stack the sphere on the A layer. On top of the A layer, we have two options, B side or C side. And on B layers, we have two options, A side and C side. So this variation of the stacking create many, many different variations in crystal structures. And these are the structures very popular silicon carbide. That's 3C and 4H and 6H. Here, the C means cubic phase, and H means hexagonal phase. And anyway, that's very interesting for pure academic or crystallographic study, but that's a big mess for semiconductor devices. We have to find one desired polytype, and we have to grow single-phase polytype without any mixing. That was a problem. And this 1990 6H was the exclusive choice because quite often 6H was grown. And that's very useful for blue LED when we consider the band gap. And but at that time, I was working toward blue LEDs. But I conceived the idea that maybe we need some novel luminescence centered. Otherwise, we cannot compete with gallium nitride. So I selected the cerium doping during the 6H bulk growth. And after the cooling down this furnace, I found the grown ingots show some different colors, a little bit different as usual. So something happens. So I examined the crystal structures, and then we found the polytype switch happens. In spite of 6H seed, the grown silicon carbide was 4H. So at that time, very little was known about the physical properties of 4H. Only luminescence study was published. So we checked mobility by Hall effect. Then we discovered electron mobility in 4H is many times higher than 6H. And we demonstrated the high performance 4H diodes. So after that, 4H silicon carbide is a default standard for electronics applications. And this is an example, left-hand side, that was the world's first high voltage 6H Schottky diode. This performance was 20 times better than silicon. And then we switched to the 4H silicon carbide. And then the performance was 150 times better than silicon. So some fonts are now converted, I found. However, we face some high leakage current problems. And this is one example. This is off state. We would like to have very low current in the off state, but we see the many high current leakage here. So at the beginning, we supposed that these high current, leakage current, come from some defects in silicon carbide because crystals were so defective, including the pinholes. So maybe defects. But after the crystal quality was improved, this high leakage current was not improved so much. So that it turned out this leakage current originates from quantum tunneling. So this problem was solved by Professor Michael Essling at KTH. They prepared this P island or stripes beneath the Schottky metal contact. By using this P layer, the electric field at the interface was much reduced. Then they succeeded to significantly reduce the leakage current. As a result, this JBS is a prototype of the silicon carbide Schottky product. So thank you very much, Michael. And next target was transistors. Main target was metal oxide semiconductor transistors, similar to silicon. And this is a slide showing the electron mobility in silicon carbide MOS type transistors. These are the value of the mobilities. We used 4 different crystal planes, like 0001. This is a wafer surface, and 0001 was backside, and 11210 or 110 these sidewall planes. And after some oxidation, the mobility value was only a single digit here. That's not working. Yeah? And so the bulk mobility is about 1,000. So we should have mobility like 200 or 300. So this is very poor, so poor. But the situation was changed very much after the interface nitridation, which was first reported by Professor Dmitriev. And in particular, this sidewall plane, 11210 and 11100 plane, we got high mobility of 100. This high mobility is very attractive for making we call trench type MOSFET. Then this MOSFET channel is formed on the sidewall of the trench. So this is one result in collaboration with Rome. And here, on the right-hand side, I show the transistor characteristics. And all these transistors are 600 volts device. And these 2 silicon-based conventional transistors. And with this, our silicon carbide MOSFET, so this red line. For example, to deliver the 100 amps current with silicon device, they need 1 volt or 2 volts voltage drop, which means the power consumption of 100 watts or 200 watts. The product of the current and voltage is power consumption. But with silicon carbide at 100 volts, 100 amps, and the voltage drop is only 0.07 volts, only 7 watts. So huge reduction of the power loss. And more recently, we are now collaborating with the Mirais Technology and the University of Cambridge. We shrink the channel structures and achieve this performance, 1.6 milliohm centimeter square and 1.4 kilovolts. This was very large device, 500 amp device. With this transistor, we can drive the EVs. Only 1 transistor, we can drive the EV. And this performance is benchmarked like this. So very high current, still we are keeping the record performance. So very promising for the future. Okay, so now I'd like to show you the present status of silicon carbide. The wafer is now enlarged quite a lot. Now industries are using 200 millimeter wafer. That's standard. And 2 years ago, several companies demonstrated 300 millimeter silicon carbide wafer. Amazing progress. And now we can find the silicon carbide transistors and diodes in many products. One example is photovoltaic inverters or air conditioners, workstations or fast chargers, and EVs, including the Toyota, Lexus, or Tesla. They achieved about 88% improvement in the fuel efficiency. In this field, 2% improvement is a big news. So 8% improvement is a really huge impact. And the trains or rail cars are also the hot topic. All these trains, including metro or even the Shinkansen bullet trains, they are now all the new models are driven by silicon carbide 3 kilovolt modules. And they achieved 30% energy saving in the train drive. It's also very huge power loss reductions. And after the very long, 10, maybe 15-year long valley of death and Darwinian Sea, now the market is now exploding. And these survey companies estimated the market in the last year was $4,000 million US, still growing rapidly. And there are several research institutes estimated the impact of silicon carbide devices. And here's the typical items of applications, like solar inverters or EVs or rail cars. They consume the power many kilowatt hour per year. And this blue one, that percentage of silicon carbide devices still very slow because it just started. But the impact of energy saving are significant. So multiply these equations, we can estimate the power loss is as large as 2.9 times 10 to 10 kilowatt hour per year, which correspond to 3 nuclear plants. That's really good news. Another topic is safety. In bullet trains in Japan, it's running every 10 minutes. And this drive unit could be 50% smaller and 30% lighter by using silicon carbide devices. Then we have big space under the floor. So they installed large lithium-ion batteries. So by using these batteries, these trains are self-propelled to the next station at the disaster without the power supply through the pantograph. This is very good news for the safety of daily life. So the summary, silicon carbide power devices now are exploding, but we need much higher quality of silicon carbide and silicon dioxide interface. Mobility is still 50 or 100, we should have 300. And understanding of device failure and degradation mechanism, a novel device structure for higher performance, also ultra-high voltage devices is next target, as Michael is also working on this subject. It's about 10 kV or 20 kV where silicon device cannot reach. This is a future target. And also, other than power devices, silicon carbide are attracted in many applications. One example is ICs and sensors for extreme electronics, like high temperature and radiation, including the Venus project. And KTH is also the cutting-edge group in this field, high temperature electronics. And also, several groups are working on quantum defect control and integration for future quantum computing. And also, the optical devices are also very interesting. You know the smart glass from Meta? This lens is not glass, that's silicon carbide. Transparent, and the refractive index is high, so the light is more confined inside the lens. Then we can get a more clear image in the smart glass. Very interesting application in the future. So now, this is my last slide. Sweden and Japan have been the leading countries in this field, and collaboration should be more enhanced. So, tack så mycket.
Thank you, Professor Kimoto. I think we have time for 1 or 2 questions from the audience. Oh, yeah, sorry.
My name is Marek Rubel from Royal Institute of Technology and Uppsala University. Thank you very much for the talk. On your last but one slide, you mentioned this radiation hard electronics.
Yes.
How do you see this also for application in diagnostics in fusion reactors?
Yeah. For example, in Japan, we experienced big disaster in nuclear plants. We need really reliable sensors. So this is one project inside Japan. That's one, maybe that near future application of silicon carbide.
Thank you.
Any further question? Yes, please.
Thank you very much. Very interesting talk. I'm Shiro Watanabe from KTH Royal Institute of Technology. And my question is about the SiC devices. And you mentioned the benefit of the power efficiency, but how about the scaling or device size? That the SiC devices contribute in that. That's a compact or any
Scaling.
the size, simply the size.
Size of chip, you mean?
Yeah, exactly.
Yeah, that's good question. Because silicon carbide contains still some defects. So the maximum size, chip size, is now maybe 7 millimeter times 7 millimeter. Then we can get high yield. When we make a 1 centimeter square device, the yield is getting low. So we have to improve the quality of the crystals as well.
Thank you very much.
Yeah.
Thank you very much.
Final question here.
I'm Björn Ekelund from Ericsson. Silicon carbide is a very popular material for high energy, high power applications, but it's not widely used for higher frequencies.
Right.
Today, consumer communications is typically in the gigahertz area, which I assume silicon carbide is not very suitable for.
No.
But is there some boundary? I mean, if we're talking megahertz, would it still be usable in that area then? Or what is sort of the usable limit when it comes to frequency?
Yeah, you are right. For gigahertz application, gallium nitride or other 3-5 compounds are much more attractive. Silicon carbide cannot compete. And maybe 1 megahertz is some boundary between silicon carbide and other compound semiconductors, also depending on the power.
So by that, thank you, Professor Kimoto, for very inspiring talk.
Thank you.
We now continue with some Swedish research perspectives on semiconductors, and this will be Professor Lars-Erik Wernersson, being a professor in nanoelectronics at Lund University, that will give that. So please, Lars-Erik.
So dear excellences, dear distinguished guests, dear colleagues, it's my pleasure to give the Swedish perspective of this, and I'll try to give an overview of what are we doing in semiconductors in Sweden. And of course, some special focus will be of Lund, of course, also since I'm coming from Lund. But if we start semiconductors in Sweden, I think it's important to think, what do we have, right? And what are the strengths and so on? And semiconductors is intense, it's research intense and so on. So it's no surprise that the big industries are actually located also surrounding the major universities or in these areas. So we have all the companies, the big companies, mobile communication, Ericsson is there, of course. We have in defense and security, Saab is, I think, worldwide known as well for this. Axis. We have semiconductor efforts in the automotive sectors, Volvo Cars, and Volvo is there. In the energy, Hitachi Energy has a strong effort here in Sweden. Automation and transport. You see, it's all right. So we're all in all the main industrial sectors. And if we take a look at the locations and so on, we can see it's, it's a lot here in the, let's see if I can make it. Maybe not. Yes, you press. Okay, thank you. Of course, so it's here around Stockholm, in this area, Stockholm, Uppsala, Rise's activities in this area. It's in the western part around Gothenburg, where there are also strong activities. We have down in the south, where we're located, Lund, close in this region. And then maybe we should also mention in Östergötland is also very strong, around Linköping, where you were when you were in Sweden, also very strong in semiconductor materials and circuit design, etc. So it's distributed over Sweden, and all the main industrial sectors are active. If we continue here, take a look at further right, where are we in the value chains? We have all the major companies are there that are using products, utilizing electronics in different ways. Maybe not semiconductor companies, but it's built-in systems. Then we have strong companies that are really doing semiconductor development and design in these. We have Ericsson, Saab, and so on I mentioned, just to give a few again. They are here. Then we come into the core semiconductor industry, that are maybe a bit lower down here on the in the value chain, how should I say it? There are a number of medium-sized companies, small companies that are important, that have the growth, also in fabrication processing. It's in manufacturing, design, EDA development, equipment development, so it's all over in the different sectors. And then down at the bottom, of course, we have the universities and the infrastructures and so on supporting it. So it's quite distributed, and we're active in all different areas. And of course, since we are a small country, we are well connected into the international community, well into the European network, but also I think it's very important to connect into the leading industrial nations, like Japan, of course, in Asia. It's very essential for us. So we're also looking into Sweden, what will we do and what are the possibilities for Sweden in this ecosystem. And of course, it's the competence and in design and production that is really key for the system design, that is essential for the Swedish as a nation, where there is strong industrial effort. But then it's also to maintain skills, to develop our competence in order to supply the competence skill of Swedish competitiveness. It's really about the people, right? It's about education and having strong research. So take some look over the activities. I have picked one slide from Chalmers University. They have a wide range, of course, but here is one example. It starts down with individual devices. In this case, maybe it's gallium nitride, HEMT devices starting at the transistor level, starting to look into how can we get power out of these devices and how can we build components, going into full power amplifier design, characterizing the power amplifiers, etc. Not only in gallium nitride, but also in silicon germanium, in silicon technology, and then going all the way into system demonstration for communication links, etc. that we are strong on. But then there is also technology development. It's further out there to the right, like integrated gallium arsenide Schottky diodes for terahertz applications. So it's a wide range covering starting from the materials, devices, circuits, implementations, etc. At KTH, likewise, very important here, with a strong effort starting for the materials, the understanding of the materials, going all the way to CMOS technology, analog circuit, mixed circuit design, up to embedded and electronics, etc. This is done in FDSOI, in-house technology, and also design. But then, of course, in this context today, it's also very important to point out here compound semiconductors, and particularly silicon carbide, of course, as it was pointed out, is really centered at KTH. And also, I would like to say in this context, there is also very strong efforts at RISE that is complementing the KTH efforts in this. In Lund, I picked one. This is one example. Circuit design is also extremely important in Sweden, and this is one area of examples from colleagues down at Lund, where, of course, we are doing different types of power amplifiers and transmitters in the leading edge technologies, both designing, getting them fabricated, characterizing, and so on, and use them for the communication examples. And there are a couple of generations coming after each other. And then maybe also what I think might be of importance is point out the mixed signal area, right? The AD converters, the DACs, etc., the design, which is critical for our system industry. We have national networks where we connect things between the universities. That's also very important, right? We take the best from different areas to really cover, in some cases, the full value chains. Gallium nitride is one particular strong area in Sweden, and that is of relevance. Starting from fabrication tools, this is at Linköping University, where they developed special growth techniques for this. Going into wafer production, also in the Linköping area at Swigan, working with the characterization of these, starting to process devices out of the material that's done in Lund in that case. Chalmers is doing the millimeter wave circuit fabrication and design for both communication and radar things. And then this is transferred out to industry with module development for industry. So this is a colleague of mine, Vanya Draksheva, is leading a national competence center from Vinnova in this area. And what is nice here is that we're connecting all the different parts in the value chain and bring the bits and pieces together. This is essential. Another competence center that is in Lund and KTH and RISE together is working with heterogeneous integration. This is starting to be one of my favorite fields. Maybe it's not that one technology will be the winner in the end, but the combination will be there. So we have to think, how can we combine it in an energy efficient way? What about heat generation, and how do we make sure that we do it in a way that they are not disturbing each other, the devices, etc. And building on that, we set up a scheme where we do some device processing for silicon CMOS devices in Stockholm. We are strong on RF side, 3-5 compounds in Lund, and we start to integrate this together with a strong industrial interest, and also together with the regions, etc. And I think this is also one key area for the future. And this is also supported from Vinnova in the Competence Center Act, Advanced Chip Technologies. I will give one example for my own research, what I'm doing in this. And we have for a long time been working with small 3-5 nanowires. There has been strong efforts in Lund. It's still not working here. But you can see there are the things, I'm coming to these things. So basically you're making vertical devices out of those. I'll explain it in the next graph a bit more. But what we realized that if you have a transistor technology, you can actually generalize it and you integrate it in certain ways. You can do many things. It's generic. So we started to apply this for quantum technology, for readout circuitry in quantum. We realized that you can do some millimeter wave circuitry, high frequency circuits building of this. One can do some neuromorphic computing and steep slope. I'll give you some examples. But the interesting point, we started to write proposals, and we ended up in a situation where all the European funding agencies started to fund different parts of this. So there is one funded program from the European Research Council, an advanced grant for the ferroelectric integration I will show. There is one from CHIPS JU on the cryogenic part, where we work with the European industry on this. There is one from the European Innovation Council, where we look into how can we harvest energy in space and transmit it into satellites, etc. So one can actually, and there is one together with IBM on extremely energy efficient switches. So by having one unique technology basis, we can apply to different fields, and you can reach out to the European community in different ways. And I think this is also one of my key messages, that Sweden is a good gateway to Europe as well, with our strong international connections in Europe. So the trick with these transistors is really materials integration. The key challenge is how can you get the 3-5 semiconductor on a silicon substrate? And this was elegantly solved by colleagues in Lund a couple of years ago with nanowire growth. Because if you have defects at this interface where you go from silicon to a 3-5, it's very unlikely that they will propagate into a transistor channel if the diameter is sufficiently small. So when you scale this to 10-20 nanometer, you can get very high quality of your 3-5 material, even though you have defects at the wafer level. And this one is what we use then to process the devices and to demonstrate really good advantage. And in this case, we demonstrate the devices down to 20 nanometer gate length without using extreme lithography. It's just deposition and etching. So we take away the lithography out of the system and get the performance in a different way. Having done this, again, I will be brief. We can play around, having a lot of fun in the lab. Here is another combination. It's a little tunnel junction, a p-n junction that is sitting there. Here the electrons can tunnel through, and we can open this and we can close this. And if you do this correctly, we are actually designing this for go below 60 millivolts per decade. That is a fundamental transistor limit. So here we demonstrate 49 millivolts per decade, because we are playing with the carrier statistics, very fundamental physics in this. But then we actually introduced also some material where we can program the polarization. So the polarization can go in the one direction or the other. It's a ferroelectric material. And suddenly we can have a device where we can switch the domains. And now we go well below 60 millivolts per decade. So we demonstrated 2 millivolts per decade. You can do extremely abrupt switching devices in this. The same device again, you can play in a different direction. If we think about the device where we know about the transfer characteristics in this way, we can find a way where we're actually using this as an amplifier. So we amplify an analog signal. But depending on how we bias it, we can change the characteristics. So it can either be a pass transistor, where the frequency goes through, or it can be a frequency doubler, or it can be a phase shifter, depending on how you configure the polarization. So basically we have in a little device here, we have a thing where we can go for security applications, because you can take this device, you can have a look in a microscope, but you cannot tell what it will do, because you need to have a security key. So you need to program it, and only in the programming you get out the function of this. So again, at the bottom here, down at the very, very fundamental bottom of how these transistors are working, there is a lot of room for innovations, new things that we didn't think of. But if we do the material integration in a correct way, then we can actually realize a lot of things. The final example is also, I think AI is an extremely important area, and the power efficiency in artificial intelligence. How do we reduce the power consumption in this? And the holy grail is the integration of logic and memory, the combination and switching between these things. So we did this also in the same structure by having integrating a little memory element on top of these transistors in a 3D configuration, where you have the transistor at the bottom to control it, and then you store the element on the top. And actually, we demonstrated, yeah, you can switch this a certain number of times. But basically, this is an outline for a 3D integration scheme for computation in the memory instead, which is more power efficient. And I think we demonstrated 200 times power reduction in this by just integration. So there are, again, plenty of innovations down at the bottom. In Lund, in general, if I summarize the efforts in Lund to compare to the others, we are very strong in nanostructures, compound 3-5 nanostructures down to the atomic level, understanding these materials and trying to find innovations in new ways of using this for semiconductor devices. I think this is the unique selling point at Lund. Finally, I made a slide, why invest in Sweden? Or maybe I should rephrase it to why collaborate with Sweden. I think it's maybe a better way. It's for our guests again, right? We have a high innovation density in this. We're good in forming companies, in particular in deep tech, and I think we're number 2 Swedish position in Europe in this. We hope and we think that our society is stable and open, like Japan, I would say in this way, the way we understand it. We also think a lot about sustainability and about cleanness of our energy system, etc. I think this is, we have a strong combination of competence and a combination also with good work ethic, but there is also life-work balance in Sweden. And finally, I think what's also important, I think we're a strong gateway to European networks. We're very well embedded and Now we see that Japan is also joining the Horizon program. I think this will open up for collaborations with Japan. So with that, I would like to thank you for the opportunity to talk here. And I say I'm very happy to do this, particularly for our Japanese guests. I've been so many times in Japan, and I enjoy it every time. Yeah.
Thank you. Thank you, Professor Wernersson. We open for a couple of questions also here. Yes, we have up there.
Thank you very much. You mentioned a few times the importance of the structure, defects. What about the purity? What is the purity necessary for these materials? Is it 4.9, 5.9, 99.999? To get really stability.
Yeah, it's a very good question. It comes back to this about manufacturability, etc., about these things. I think a good way to answer this one is that our devices are working. The devices are working the way we want them. And maybe we're happy, sufficiently happy. But of course, if we would go down the road and you go for manufacturing, I think these things will show up, yes. And this is also one maybe challenge we're having in Sweden. We run a lot of our experiments in university labs, which are open to students. And in the international competition, this is also giving us some challenges because we don't really have the infrastructure needed to really take the next step.
Any further question? Yes, please.
Hi, thanks for the presentation. Kind of building on the comment that you just made, the step from lab scale research and finding results to industrially relevant research and results. If you could ask something to the Swedish government or institutions, what type of facility and capabilities would you like to see built in Sweden within your line of work in the next, let's say, 5-10 years to really compete on a global scale?
Well, I think I would answer in this. I would like to see a lab-to-fab strategy. I think this is the key thing that we're lacking in Sweden. I think we could expand a bit on the university capabilities, but it's not the university's role to really do this. We should also look into what capabilities are in Europe so that we don't duplicate it. When we have done these exercises, maybe there is something left where we can invest in Sweden as well.
So by that, thank you, Professor Wernersson, for an inspiring lecture. In the third keynote speech, the focus will be on business development and on building and supporting collaborations. Mr. Gamada, which is the Deputy Director General of the Japan External Trade Organization, JETRO in London, will give a keynote on Japan's current national international policy and JETRO's activities. So please, Mr. Gamada.
So thank you very much for your kind introduction. So my name is Gamada. I'm Deputy Director General of the JETRO London office. And I'm basically in charge of the innovation promotion in the European nations, as well as the entire, UK and the Nordic regions, including the Sweden. So it is my great honor to be here to present Japan's latest policy trend relevant to the semiconductor this time. So before moving into detail, please let me shortly introduce ourselves. JETRO is a government agency promoting under the Ministry of Economy, Trade and Industry, or METI, promoting the mutual trade, investment and innovation between Japan and the rest of the world. So we have more than 120 offices in both overseas and in Japan, including the 16 offices in Europe. So and our London office is the regional headquarters, again, covering the Nordic regions, including the Sweden. And our latest office in Ukraine in 2024, and I have also traveled several times to both Kyiv and Lviv, our area, to support their innovation. So currently, we have the 4 pillars of activities, and the largest sources have been, say, allocated to the first pillar, which I'm belonging to, the facilitating the innovation. So under this innovation pillar, we have 2 main programs. The first one is the Invest Japan promotion. We are, say, designated as Japan's national investment promotion agency, facilitating the European startups and the tech companies' business expansion to Japan. And another program is for the open innovation collaboration promotion, the J-Bridge program. They're supporting more than 1,900 Japanese clients now. We are connecting such corporates to the startups, academia, and ecosystem builders to solve common social and economic challenges. So now, let's move on to the policy side. As slightly introduced by the ambassador, as you might know, around 2 weeks ago, there was a general election in Japan, and the Liberal Democratic Party won seats in a landslide victory. The number of the seats they got is the highest in our history. And with this huge win, our Prime Minister, Sanae Takaichi, formed her second cabinet to steadily implement strategic areas actions. So here you can see the 17 industrial sectors which we will be heavily invested in. And on the top of the list, AI and the semiconductor appears here. Also, as usually imagined, several microelectronics-related industries are also in the list, including the quantum, cybersecurity area, defense and advanced material development, and others. So important thing here is that the cabinet ordered to prepare multiple, that comes, yes, multiple years funding. So this is not quite usual for the Japanese budget structure. So to support these strategic sectors investment, which greatly contribute to the business predictability and its growth. So also, there was also quite important action between EU and Japan last year. During the 30th Japan-EU summit, the leaders adopted the EU-Japan Competitiveness Alliance, which aimed for the jointly pursuing the strategic autonomy with 2 like-minded nations. There are several keywords here. First one is the resilience of the supply chain. Yep, around here. Yep. So as written in the EU competitiveness compass, which published last year, one of the biggest challenges for the EU is its heavy reliance on the key critical minerals, parts and the components to the single country in Asia, not Japan. So with this alliance, Japan and the EU agreed to, say, diversify procurement sources, which lead to the possible restructure of the existing global supply chain, meaning that there are huge business opportunity to restructure such as a supply chain. And the second one is the digital, which I'll touch upon later as EU-Japan say digital partnership. And the third one is the research and innovation. So for this pillar, JETRO and NEDO is our sister organization, Japanese funding agency of Japan. Funding agency. It's specified say key organizations to deepen collaborations with European Innovation Promotion Agency and the Horizon Europe. Namely EIC, European Innovation Council, and the European Institute for the Innovation and the Technologies, EIT, as well, through supporting respective startup growth. So, as introduced, by mentioned several keynote speakers here, regarding the Horizon Europe, yes, we finally joined. Announced official participation in the Horizon Europe in the 22nd of December. So to the Horizon Europe Pillar 2, the Global Challenge and the European Industrial Competitiveness Pillar. So while we need to wait for the Diet's approval for the actual implementation, we have received great attention from the Japanese academia and the businesses. So I'm personally receiving more than like a 15 tangible interests from the Japanese companies. And as much as 1,000 participants gathered to 2 Horizon Europe webinar this month. It's a huge attention. So however, for the Japanese cooperative who is quite new to this framework, there's a common challenge to identify the best consortium partner to jointly applying the code. Yes, so in this regard, JETRO will be developing the national contact points networks with the major countries, including Sweden, possibly, for such a partnership development for both the Framework Program 9 as well as the Framework Program 10 from 2028. So, please let me go into detail about the semiconductor sector. So EU-Japan Semiconductor Cooperation has been done, and the EU-Japan Digital Partnership launched in May 2022, covering semiconductor beyond 5G, high-performance computing and quantum, and the cybersecurity field. So from Japan, 3 ministries, namely the Digital Agency, METI, and the Ministry of the Internal Affairs and Communications, joined this partnership. So based on the digital partnership, there were ministerial council meetings on your right held annually, and at the 3rd council meeting, both sides confirmed interest in conducting collaborative research project in sustainable chemical alternatives, including PFAS, and heterogeneous integration and the chiplet devices, as well as the process development for the beyond 2 nanometer logic semiconductor. So however, as far as I understand, under the CHIPS joint undertaking actions, Korea and the EU already launched such collaborative research project focusing on the heterogeneous integration again, and the new neuromorphic computing technologies. So I really look forward the tangible announcement of the from Japan for the research project very soon. So next, I explain the current structure of the Japanese semiconductor strategy. So ongoing semiconductor strategy originally announced in 2021 and revised in 2023, while there was one more revision in 2025 focusing on the AI and its possible effect on the semiconductor field. But since the fundamental structure is the same, I have developed this matrix of technologies based on the strategy in 2023. So under this strategy, METI focused on the logic, memory, specialty semiconductor for industrial use, advanced packaging, as well as the equipment, parts, and raw materials manufacturing. And divided the timeline into 3 phases, or the 3 steps. So step 1 is the actions based on the ongoing demand to secure production base in Japan, including the government support to the Kumamoto area for the TSMC, or in Japanese factory name, JASM, foundry development, as well as the Micron Kioxia collaboration in the memory development field. And step 2 is up to 2030 for the establishing the next generation technologies. Here, Rapidus comes towards the 2 nanometer logic semiconductor production. So also the establishment of the chiplet technology and the advanced material development toward beyond 2 nanometer semicon production is also targeted here. And step 3 is the beyond 2030. The future technologies such as the photoelectronic fusion, embedded memories, GAN or the GA203, power semiconductor development, and optical chiplet appears here. So for this future technology development, Japanese government also developed LSTC, or the leading edge semiconductor technology center in 2022. So Let's talk about the Rapidus and the LSTC. So Rapidus established in 2022, aiming for the 2-nanometer logic semiconductor production base. And after the incorporation, what they did first is to collaborate with IBM. So through the strategic partnership, Rapidus announced to introduce IBM's 2-nanometer design and process, and sent nearly 150 engineers to their laboratory in Albany, New York. So actual factory site development, named as the IIM-1, started in September 2023 at Hokkaido. And last July, Rapidus announced the successful test production of gate-all-around transistor and attaining electrical characteristics on it as its targeted milestone. So based on such steady progress, also by strong push by METI, I would say, by this month, more than 30 companies decided to make the capital investment, capital participation. So especially the companies appears here, announced further increasing the amount of the capital injection to deepen partnership with Rapidus. So on the other hand, LSTC also established in 2022, as I mentioned, participated by the leading national research institutes and the universities. So based on the open calls by NEDO, funding agency, again, under METI, they are developing the several key technologies, including the equipment to enable short turnaround time and the clean processes, edge AI accelerator development, in collaboration with the 10th rent of Canada. So Rapidus and LSTC is a kind of the twin brother. So while LSTC supports research and innovation process and injecting the outcome to Rapidus, Rapidus also shares priority development needs to the LSTC. So now finally, please let me introduce what we JETRO can do for your business. Currently, we are prioritizing the technologies and the microelectronics, life science, and the decarbonization field for our Invest Japan and the J-Bridge activities. As for our Open Innovation Program, the J-Bridge, we will be promoting the Japanese corporate participation to any Horizon calls. And as we will also organize academia-focused business matching event with Japanese companies, especially focusing on the tech transfer and the startup support functions as well. And in terms of the Invest Japan, in the past 2 years, we have been supporting EU's business mission program, EU Business Hub, to send 50 startups and SMEs to the Semicon Japan, which include several Swedish companies. And we conducted dedicated business matching event day before the exhibition. Also, we are also planning to invite Europe's deep tech venture capitals to Japan to provide the opportunity to meet with the excellent academia and the semiconductor innovation ecosystems. While these are the project-based approach, but we are also developing various tools, various support menu to support your business expansion in Japan or business collaboration with Japan. So that is all from my side. So thank you very much for your attention.
Thank you, Mr. Kamada, for an inspiring talk. We're open for a couple of questions. Yes, please. Over there.
Is it working? Yes, thank you. I'm a little bit curious about the financial side of this. As you know, this industry has an enormous capex challenge. So I'm thinking, how do you think about turning capex into opex? And also, if you are looking into what is called digital asset with blockchain and these technologies, because it potentially can create a dynamics in the financial system. Is this something you're looking into?
Yes, thank you very much. Yes, that is the common challenge for all the semiconductor sectors in the world. And in Japan's case, we have injected nearly 15 billion euro only to Rapidus. So that is our strong commitment to support the CapEx side and launching a project. So we will be supporting the Rapidus until around 2030. And after that, maybe OpEx, some of the elements for the OpEx side support can be also considerable through the, like I say, tax incentives. But we initially just focused on such a subsidy side to support the CapEx side. And for blockchain technologies and its application, sorry, could you just clarify your point? Sorry.
I don't know. Have you heard about tokenomics? All right. So you can tokenize certain aspects of the machine, for instance, and that created a new dynamic, financial dynamics. And these are called digital assets, tokens. So that, so I'm curious if you're looking into this area when it comes to financial models for the industry.
Yep, thank you very much. Sorry, I did not have much knowledge about that context, so maybe just talk a bit more after this conference. Thank you.
Thank you.
Second question.
Thank you, Gamada-san. I think just short questions here. The capacity of the Rapidus facility, did you mention what is the wafer capacity in that kind of fab? And also you had the 30 plus investor companies. Did they also sign up for not just investing, but did they also guarantee a sort of purchase volume from that Rapidus facility? Do you know that?
Yes, thank you very much. Sorry, as for the capacity, sorry, again, please let me check and revert to you. But they are very steadily, preparing for the 2027 launch of the full implementation of the first factory. So I'll check its capacity. And for the investment relationship, yes, of course, for the Rapidus establishment and its operation, a lot of the Japanese companies are very deeply involved into that initiative led by METI. So it totally depends on the company's action, but at least several of them are further committed more than the capital investment, I would say. Sorry.
Thank you.
So Bharat, thank you for your inspiring presentation.
Thank you very much.
We will now have a panel discussion. So I will ask the panel to step up on stage. It's a big panel, as you can see. And some of the persons in the panel you recognize from the keynote speeches, Professor Kimoto, Mr. Gamada, and Professor Wernersson. But we also have Björn Ekelund, you presented yourself with a question from Ericsson. We have Lars Gustafsson from the Swedish funding agency Vinnova, Charlotte Samuelsson being with Mycronic, Elisabeth Österlund, Swedish Electronic Trade Organization, and Mikael Östling, KTH. So let me start here just with an open question to all of you. What do you bring with you from what you have heard during the keynotes? Is there anything particular which you feel is important and you take with you? What has inspired you? 3 answers.
I think this is on, yes. I can start. Coming from Ericsson, I think I was really happy to see photonics be mentioned in one of the last slides here, because before Christmas we announced a major investment in Japan with a new R&D center in Yokohama with over 300 engineers. And one of the research topics, that will both be product development and research. And one of the topics that we will focus on in that center is actually photonics.
So, spending my whole life in this business, I know basically what we can do together. It takes time to build relations and to build the research infrastructures and so on. We heard from Professor Kimoto that you started with nothing. You had to shape your own wafers. We are still on shaping wafers to have the quality that we need for scaling up the capacity of each chip. That's continuous. It's not ready. It will take many more decades before it's perfect, if ever. So what I see is basically that Sweden and Japan can work excellently together. Now when we have maybe the new instruments by Japan joining Horizon in a better way. So I think it's open for us to just tie up all the connections that we have developed over the years and do things also with impact from Japanese industry, telling us what they see as important thing, and we can take the Swedish industry and combine that. So I think collaboration is the essential thing here.
Mr. Cabana.
Sorry, thank you. So I'm very impressed by the huge Swedish semiconductor ecosystem comprised of nearly 1,000 players. So it's a huge number. So it's a kind of the huge, like a hidden gem for the Japanese investors at this moment. And since one of our clients is the Japanese companies in Europe, which is focusing on the tech sourcing, and there are around 100 companies having such as a function for the tech sourcing. But there is only one or two staffs allocated basically in one company covering the entire Europe or even to the EMEA region. So for them, it is quite essential to get to know about this huge ecosystem existing of this kind of the ecosystem itself. So as Jetro, maybe later on, maybe I'm having the some idea to having some industrial tour or something from among the Japanese companies in Europe to Sweden. So that is my commenting.
Thank you. Who wants to continue?
So I think that what already have been said, I think the collaboration that is possible between Japan and Sweden is really something that we could build on. I think the culture is quite similar, the way of working long-term, closely, stay together, working with the consensus style. I think this is a very nice foundation, both from a competence perspective, but also from a culture perspective. And I'm happy to see all the possibilities that comes with Rapidus and the great holistic perspective working from the very far back end to the leading edge front end in manufacturing.
One thing that strikes me when discussing with Professor Kimoto is the stability in the university operation. We can see we are living from grant to grant to grant in Sweden. I'm not complaining too much, but it doesn't a bit, but it doesn't give us stability to really search for long-term issues. We are very dependent on the next and the next call. So I think we should look into the Japanese system, funding the professors, not too much, but in a secure way. So I think we have a lot of things to learn there. That's what we should give the message to our government.
Professor Kimoto.
Right. Yes, yeah. In Japan, maybe one striking difference that professors don't have to pay for the students, even PhD course students. I don't want to say, please follow the Japan. No. It's important to support students. In Japan, like JSPS fellow or many other big scholarship from foundations. Such funding quite now improved compared with maybe 10 years ago. Now students are really getting rich. So professors can get some funding. Almost 100% of this budget can be used for pure research, not for student scholarship or salary. And which means the subject of research is not less affected by the proposals. So more free, we have more
stable, long-term.
Stable and long-term research is possible in Japan.
Sounds good. So, who wants to continue?
Yes. Okay. Yeah, thanks. So I'm Lars Gustafsson, Vinnova, and we'll come back to this discussion about the the long-term funding. Now, I wanted to reflect on something that was mentioned, and it's one of the keys when it comes to increase and enhance the collaboration between Sweden and Japan. Is very much in networking and getting to know each other. And I think something that was mentioned that is a very, very good idea in the long term is to use the possibilities in international funding provided by the European Union and the member states. So AgriSense, I would like to mention, that is a project which is 50 million euros. And it's led by a Japanese company with a subsidiary here in Sweden called Komatsu. That's Komatsu Forest. And it's very much in line what we want to achieve within the development of sustainable society in Japan and Sweden. So it has a focus on using technology, new technology, testing out semiconductors for sensing applications and communication for forest industries, to increase sustainability when it comes to biodiversity, but also in agricultural development of sensing technology, including then partners from Sweden, Finland, Netherlands, and a number of other countries. So this type of collaborative projects are important. Then I agree on that Horizon Europe is something we need to work on together to get a better partnership. We sure will do that. Nevertheless, I would like to point out that when it comes to networking, actors like SSF Foundation here in Sweden are important because they are long-term, they have long-term initiatives. They might not be big, but they're important in order to start to glue the systems together. And also Vinnova have a role to play. So we've had smaller type of projects together with Japanese counterparts. So these are important. Thank you.
Yeah, I would like to continue on that along that line. I think these glues on the academic level are really good starting points. And when I was a PhD student in the 90s, there were actually strong collaboration exchanges between Sweden and Japan, and that fostered a culture that I think has been really exciting. And I think attracting young people into semiconductors is a key, right? At least in Sweden. And by bringing the Japanese, I'm sure that we will attract further students into this, right? The connection to Japan, because it's an exciting country in itself. So I think we have lots of benefit. And then also I would agree on the company-company interaction. I can give also very good examples of startup companies in Sweden getting engaged with medium suppliers in Japan, and then the final end product in the car industry and automotive is in Sweden, right? Lots of these things that are strong for the development of the companies.
Thank you. Elisabeth, would you like to add reflection?
Yes. So what struck me is that when I look at and listen to the Japanese strategy, 40 years ago, Japan had more than 50% market share in the semiconductor business, and a couple of years ago, Japan was down to 10% market share. But what we see now is that it's such a huge commitment, and it's a clear strategy, and also it's not only about the ambitions, but also about the execution. And from the Swedish side and all our companies, we also, of course, welcome that you focus on building up manufacturing capacity. We also, you mentioned, it was mentioned here, the EU Business Hub visits to Japan. So we visited together last year with 5 Swedish companies, and we look forward to also visiting this year, I hope, with several Swedish companies. So thank you very much for everything today. Very interesting.
Would you like to add something?
Yeah, well, I think also from the Japanese presentations, we also saw that you have a diversity of technologies. Of course, we are very impressed with the 2 nanometers or beyond technology. To be honest, we cannot fill those kind of fabs here in Europe yet. But what I see there is basically that there is so many different shades of semiconductors and so much to gain from the sustainability point of view. So Professor Kimoto showed some numbers there, and that was very moderately stated. There's so much more to gain by rolling out these power semiconductors. And then we say, should it be silicon carbide? Should it be gallium nitride? It should be both. And it should be silicon. We are not here to say this is the best, because we need all the different technologies. We need to understand that. And we have a common knowledge on how to do that with the materials, with the characterization, with the design. It is basically the same technology, but with different material parameters. So we shouldn't be too scared of saying, are we really choosing the right thing? We have to look into what is coming, because in 5 years from now, we don't know what is the hype coming. We can guess. Some will guess the right thing, but we don't know, and for sure not for 10 years. But we need to be alert, and we need to have the technology to take on whatever comes up.
So both our countries are in a process in different ways, but strengthening the semiconductor area, and several of the speakers and also in the answers from here talk about opportunity in increased collaboration. So what is, to your opinion, the first thing we should do that is tomorrow? Today.
First thing tomorrow is to have breakfast. And after having breakfast, we should consider to see how we will take the next step to enhance collaboration and between Sweden, Japan and EU. And I'm very glad that it has already been mentioned that there is since a couple of years back, a Japan-EU digital partnership, right? So we need to strengthen that further. And one of the instruments that I'm personally looking forward to be implemented and applied is in the CHIPS joint undertaking. So I'm assigned by the Swedish government to be the main representative in the CHIPS JU and the governing board. And there we are planning for a joint call with Japan. It's a 15 million euro budget from the EU side. And we hope that we can stitch this together with Japanese counterparts in due time. I'm pretty sure there will be a call. There are some challenges when it comes to getting into a final agreement when it comes to the scope of topics and also budget and the evaluation aspects of the call. But I'm very convinced that we will have this together. And this is a very good cornerstone for the further development into practical applications in Horizon Europe. So, and I think the Digital Week in Tokyo at the end of March there will be some meetings regarding this call. And one of the tools for the joint undertaking and the Commission is a CSA, a Coordination Support Action, with the name of Jasmine. And I'm certain that there will be participation from that CSA, and hopefully we can close the discussion and open up a call in July, which is now currently the plan. And in that topic, referring to what Mikael said, it should really be possible for having the interactions like with Professor Kimoto and your colleagues in the field of silicon carbide and power electronics. So we are working on that. Thank you.
Very good. Very good. I'm not just speaking about money, but we have also to understand that what we have done in Sweden over the past 2 decades or 3 decades, we have built a fantastic infrastructure. We are not starting from scratch. We have very good foundations to continue to support that. And tomorrow we should send a letter to the government and say, yes, co-fund the European action, because that is what it takes to be in the CHIPS joint undertaking. It's not big business. It's safe money to do. And that's the first thing we do. The second thing.
I think these are great actions proposed, but I think when it comes to starting Horizon 2020 projects, or 2030 maybe, or Horizon Europe projects, sorry, it takes a while. What we could do literally tomorrow is to start exposing the Japanese and the Swedish semiconductor ecosystems to each other. I think Amada-san was onto something really interesting with the tech sourcing. And I think both Japan and Sweden could benefit greatly from being much more aware of the different the players, the companies, the startups present in both areas.
Yes, actually I visited the KDH yesterday, and I saw the very fantastic infrastructures about the semiconductors. All kinds of materials, not only silicon, and from material growth, characterization, and process and device, and both electronic devices and photonic devices, or even MEMS. And this infrastructure is open, almost open to public. Very amazed. I don't see such infrastructure in Japan.
And now you only
so
saw
must
the
be
PH one. Yeah. And we have 3 more.
It's very good to start.
I think that what we need to do tomorrow is to accelerate young people to join this community or this field of technology. It's so sticky, it's so interesting, it's so, look at us. We have been... So I think that we need to get the young people in, because they will stay and they will solve all this stuff for us.
Yeah, I think about funding, short exchange visits for students, etc. I think this is also a way to get going on the lower level, but this will drive this for a long time to come, right? And we could do that directly after our breakfast tomorrow, yeah.
So thank you. So as for the Horizon Europe program, as I mentioned, we are getting quite a lot of the inquiries from the Japanese companies, including the several top semiconductor companies as well. But their common challenge is to find out an appropriate partner. So as mentioned by the professor, actually my idea is also collaborate with Sweden as a gateway to the EU. Yeah, that is maybe the quite important part. So, since there are several key university professors here, so what I should do is to exchange my name card. And then maybe since especially for the cluster 4, that is the like I said, industry and semiconductor, including a pillar of the Horizon Europe. And this year's call would be closed within maybe May. So that is quite soon. So we have to find out the appropriate partner either for this year's call or the next year's call or the beyond. As we all know, our say framework program 10, the budget amount would be doubled. So that is the huge opportunity for the Japanese companies to jump in. So for that preparation, including the Vinnova, it is quite important to maybe say develop some Swedish Japanese companies collaboration first to say nurture such as a common say sense within 1-2 years to apply for their next FP10 together. So that is the maybe not tomorrow's action, but yes. Thank you.
But almost.
Yeah, that's great to hear. Yeah, it just happens to be so that I'm also the Swedish representative from Vinnova in Cluster 4, Digital Industry and Space. Now, when it comes to companies, one company that is active when it comes to collaborative project, which is Japanese, but is located in Sweden, and they are very successful. They're hiring hundreds of people every year right now. That is Hitachi Energy. And they have, of course, counterparts in Asia, including Japan. And once the conclusion of the association of Japan with all the nitty-gritty details is there, this is one company that can be of, so to speak, good use, and they can have very good use of Horizon Europe, both in Japan and their subsidiary in Sweden, but they also have other subsidiaries in Europe, including Germany. So that is one example of a company. Another interesting development when it comes to semiconductors, when it comes to applications, that is the fact that SoftBank, the Japanese investor, has agreed a deal with ABB to acquire ABB Robotics, and their main hubs in Europe, in the world, is in Sweden. And I'm quite certain that I know that ABB Robotics are interested, of course, in sensor development and also in semiconductor development. And with SoftBank as owner, kind of partner also, that opens up for a very good collaboration between Japan and Sweden. Thank you.
Thank you. Anyone else that would like to add?
Just mentioning, not regarding Japan, but I hope that when we get into discussions with Japan on funding, maybe bilateral funding and so on, that could be a rather quick process, because I'm a little worried when I see the CHIPS joint undertaking and the procedure to get through and to get your proposal granted. That is not an easy task, and I think that's maybe something that we also can alert our government or officials from Vinnova and others to help out, because as a professor I feel where to start. Can I really spend this time on setting up such a project? So we have representatives from RISE over there. So I think they are very professional in setting up this kind of proposals and so on. So we have to learn how to collaborate with organizations that are maybe more suited for big proposals than the universities themselves, with some exceptions, of course. But I see that we have such an administration to get these projects flying. So I'm afraid that sometimes you say, okay, it's not for me. I cannot take the time to do it.
Rick?
Maybe two additional areas that we didn't talk so very much about is advanced characterization. I think Sweden has a strength, right? MEX4 is in Sweden, and the European spallation source is coming up. We can apply that to different types of semiconductors, understanding their material properties in depth and also the device operation. And then one further aspect I find extremely important is advanced packaging and the characterization of the advanced packaging. And there I think RISE is the player in Sweden that has the strongest competence in this, and it's extremely important.
May I just advise you that there will be a conference 9th of June in Stockholm, in Kista, Nordpack on packaging. I'm leading a panel, as it looks. I'm not a specialist. I was asked, can you moderate? Yes. Now I have to find all the invited speakers. But there we will look at packaging from quantum. How can we get the quantum into a chip? How can we package the power devices? How can we package emerging devices? And how to understand the whole heterogeneous integration scheme. So that's just a recommendation if you want to learn more about packaging. There is a whole conference.
So time's run, so I thought I should open up questions from the floor to the panel. If there are any questions you would like to listen to this fantastic group of representatives, so please. Yes, please.
Thank you very much for the panel. I'm Jeanette from Vinnova, NCP for Cluster 4. I have a question to you, Björn, about Ericsson and your research center is now initiated in Japan. We talked about the next generation. Are you intending to have industrial PhDs or postdocs that maybe are doing their research in Japan and Sweden? Because I think this is such a great opportunity for the future.
Obviously, we have industrial PhDs, and we also employ postdocs from time to time when there are mobility grants that are suitable. We also intend to employ PhD students in Japan. Having them move back and forth, we haven't really decided on yet. But that is very likely to happen because we are an international company and we rely very much on sort of human knowledge transfer, meaning that people actually meet each other and talk. So I think that you can probably assume that we will do, yes.
I think we have a question there, yes, please.
Yes, so I'm Björn Hansson representing Exilum, a small company here with about 90 people in Kista. So I think we heard a lot of perspective from the academic side and from the large industry side, but as an SME, I mean, we already collaborate with Japan as well as we can, but typically you have less resources. So do you have any comments on how to help specifically smaller and medium-sized enterprises to collaborate with other SMEs in Japan or large companies in academia in Japan?
Just one quick answer is that now Sweden has a Vinnova-funded and EU-funded Swedish Ship Competence Center that has a task to help small and medium enterprises to access for example, the pilot lines within EU. We have 5 major pilot lines and 6 on quantum. So that's one thing that should help your kind of sized companies to get hold of the technology there. And also to our Japanese friends, I think it should be open for anyone to work with these pilot lines. So if we can be the gateway to that, that's also one way in, I think. I'm not sure if I'm telling too much, but I think it should be possible.
I don't know if this is the answer to the question, but I think that in Mycronic we have been working with Japan for 40 years maybe. And we did it when we were a startup like 50 people, or now we are 2,000. And we continue to have a very high mobility to secure that we have people moving between the companies. We have expats, we have impats, we have, I think all this type of moving people is quite easy to do with Japan. We have, as I said, same culture, same ability. And through that, there is also organization in Japan that we can utilize to build a network for further collaboration. It could be supplier that could help out in certain areas. It could be different type of supporting each other. So I think there is a lot of networking, or not networking, but more relationships and partnerships that you can use to build a stronger combination.
Lars-Erik.
Yeah. So I'm passing on here to my next person, right, Lars Gustafsson, and the other colleagues at Vinnova. I think there are national programs on business-to-business collaboration with certain countries, and I think that might be a good scheme. I've seen good examples in other cases, but it might be a good scheme also to Japan, because it's connecting it in Sweden into the larger ecosystem of relevance. And this could actually be also a scheme for Japan that might be working very well.
So, Elisabeth, yeah, John, Lars, would you like to comment directly on?
Yeah, regarding the question from Exilum, one resource that is available when it comes to getting integrated into Japan ecosystem is to utilize the service that, to some extent, is available for SMEs, that is in the Swedish embassy. So there is a former colleague of mine, Lars Hammarström. He's kind of running the Office for Science and Innovation in Japan. So say hello from me, talk to him.
So, Elisabeth, the final comment from the panel.
Okay, just a short comment. I think that doing business with Japan, my experience as well, is that you need to have patience, and you cannot expect that the Japanese companies are open, that they give all the information immediately. You need to build a trust to get that. So, yeah, that's maybe not the answer, but it's a short comment at least.
So by that, thank you very much to the entire panel for all of your wise comments and recommendations. So thank you. So by that, I hand over to Professor Schwag-Serger for some closing remarks.
So, I want to thank all of you for coming. I think this has been an excellent showcase of a really important enabling technology, first of all. Secondly, of the research strength in both Japan and Sweden, of the huge innovation potential and broad application potential of this technology, but also of the potential in the collaboration between Japan and Sweden and the complementarity and what both countries are doing. And I think, as Mr. Gamara said, also the ecosystems, the importance of these ecosystems that exist in both countries. I also think it's a very good showcase of organic collaboration that has been growing over a long time. And I think this was something we talked about. This is not something you do overnight, neither the research nor the development, nor building the trust and the partnerships. So I think this, again, is a very important testimony to the value of this kind of collaboration that has been going on for a long time. And also perhaps a really good time for the association of Japan to the framework program, because this is there we can build on what we already have between Japan and Sweden, and that is what I'm hearing from also this seminar today, that we should really do that, and not least to try to strengthen also the innovation collaboration, build upon the research collaboration and strengthen the innovation collaboration, and that we have, again, not just a solid foundation in the research, strength and collaboration, but also in the commercial and industrial partnerships that we have between Sweden and Japan that we can build upon. So I leave this seminar with a lot of hope, and I see a lot of potential. I also take with me, and I think that's a very important message, the importance of getting young people into this field, because it is important for the future, I think, of both countries and also for Europe as a whole. I would like to thank the Japan Society for the promotion of science, for the excellent collaboration and making this exchange possible, and for their continued commitment to strengthening research collaboration between Japan and Sweden. And I think, again, this is a very important testimony of those efforts. At EVA, we strongly believe that dialogue across disciplines, sectors, and borders is essential to shaping the future And today has been a very good example of that. So I would now also like to warmly welcome you all to continue this conversation during the reception, which is generously hosted by the Swedish Foundation for Strategic Research, SSF, which we are very grateful for. And the reception will be 2 floors up, so it's not where sometimes our receptions are, but it's in Iva's banquet hall. So please join me for that, and thank you all for coming and for this seminar, and see you there. Thank you. Stefan. Thank you, Stefan.